Hello everyone, I am Damla. Our project is called Cyanobacteria for Circular Carbon Economy, and it's about how tiny organisms can help us tackle one of the biggest problems we face today, which is carbon emissions. So let's start with the problem. Carbon dioxide levels in our atmosphere keep rising, and this is a major cause of climate change and poor air quality around the world, as you all know. Most current carbon capture methods are expensive, need a lot of energy, and aren't practical for large scale use. So that's why we are focusing on cyanobacteria, which is tiny photosynthetic organisms that naturally absorb carbon dioxide. We are working with two specific strains, which are UTEX2973 and the newly developed UTEX3222, which grow fast and have strong carbon absorbing abilities. What's really exciting is they do not only capture CO2, but they can also be used to make biofuel, so we get both carbon reduction and clean energy from the same system. Here, our plan is to grow these cyanobacteria in bioreactors, where we can control the environment to help them survive and multiply. The carbon dioxide they absorb will later be turned into biofuel through further processing. Why does this matter? Each year, human activities release more CO2 than the Earth can naturally remove. As you can see in the figure, in 2024 we hit a record high, which is 422.7 parts per million, which is the biggest single year increase ever recorded. To put this in perspective, today's atmospheric CO2 is 50% higher than it was before the Industrial Revolution. Also, over the last 60 years, the annual rate of increase in carbon dioxide has been about 100 times faster than the natural rises that occurred when the last ice age ended. And the pace of change is terrifying actually. And it's not just the air, our oceans are absorbing a lot of this extra CO2, which makes them more acidic, about 30% more than before industrial times. This threatens marine ecosystem and the people who depend on it for food and income. So in short, our project offers a natural, low energy and scalable way to reduce carbon in the atmosphere, while also creating clean fuel. We believe it's a promising step toward a more sustainable future. Thank you for listening.
Hello everyone, I am Yunus Emre. I will start by explaining the intellectual merit of our project. Our idea is using cyanobacteria as a natural and sustainable way to capture carbon dioxide from industrial emissions and convert it into biofuel. Compared to traditional carbon capture methods, which are often expensive and energy intensive, our biological approach leverages photosynthesis to absorb carbon dioxide efficiently with minimal non-renewable energy use. The core of our project is designing bioreactors that create optimal conditions for the bacteria to grow and function at maximum efficiency. Alongside reactor development, we are also working on improving the strains through targeted genetic modifications to enhance their carbon uptake. Instead of focusing on one area, our approach integrates synthetic biology, reactor engineering, and environmental modeling to create a complete optimized system. Now, regarding innovation and creativity, what sets our technology apart is the combination of biological and engineering methods that improve both efficiency and sustainability. Our cyanobacteria-based systems that captures carbon faster and with lower energy costs than conventional methods. We also apply advanced genetic techniques to boost the bacteria's natural carbon absorption, making the process more scalable and cost efficient. One of our key achievements is increasing the conversion rate of solar energy into biomass, outperforming typical biological carbon capture systems. In summary, our project offers a greener, faster, and cheaper solution to reduce industrial carbon emissions and produce renewable energy.
Hi, my name is Ali Lashin, and I will be discussing the goals and objectives of our project. The main aim of our project is to develop a technology using cyanobacteria that can both capture emitted carbon dioxide during industrial processes and reuse it for energy generation. To achieve this, we have divided our project into three separate phases: research, experimentation, and application. In the research and experimentation phases, we will work on three different parameters of the bacteria and attempt to improve them. The first parameter being the bacteria's energy requirement for carbon capture. The minimum energy requirement is around 122 kilowatt-hour per ton carbon dioxide. However, real-life processes operate at up to 20 times this minimum. Our aim is for our process to run at around 6 to 8 times this minimum, which is the threshold at which we approximate it starts to become profitable. The second parameter we work on is the solar energy conversion ratio. The efficiency of cyanobacteria in solar energy conversion is between 1 and 3%. However, in order to compete with similar technology in the market, we need to bring it up to between 15 and 20%, which is the efficiency at which photovoltaic cells operate. The last parameter is the bacteria's doubling time. Cyanobacteria have achieved doubling times of down to 2.2 hours. However, we will not try to improve on this time. We will simply attempt to achieve it and integrate it into a bioreactor environment. Next is the application phase. The application phase is divided into two phases. The first one being prototype development, where we develop different prototypes to be used in the second phase, which is industrial application testing. As for the time, our project will span a total of 3 years, the first two of which will be allocated to research and experimentation. In research and experimentation, we will allocate 8 months to each parameter, although that may vary as the project progresses. In the application phase, which will span the last year, the first 3 months will be dedicated to prototype development, and the last 9 months will be dedicated to industrial application testing.
Hi, my name is Yusuf Kerem Shafak. I will be discussing the potential impact and benefits of our project. This topic can be approached under three main titles. Starting with carbon emissions. The ongoing rise in carbon dioxide emissions, which has reached billions of tons per year, have accelerated global warming and amplified air pollution. Conventional carbon capture technologies are often costly, energy intensive, and unsuitable for large scale application. These inefficiencies impact both environmental health and industrial profitability, calling for more sustainable and economically viable alternatives. Our project addresses these by using cyanobacteria as a biological solution to capture carbon dioxide, mitigating climate change effects while reducing energy and operational costs. Then we have renewable energy. Cyanobacteria present a renewable path for both carbon capture and biofuel production. These microorganisms naturally absorb carbon dioxide during photosynthesis and can be engineered to improve biofuel yields. Our design focuses on integrating these strains into custom photobioreactors optimized for light absorption and mass transfer, thereby enhancing their productivity. With a growing global emphasis on sustainability and clean energy, such biological systems offer scalable and eco-friendly solutions, aligning perfectly with the expanding renewable energy market. Lastly, we have future prospects. The novelty of our approach lies in genetic modification using recent technology to improve the cyanobacteria's efficiency under industrial conditions. We aim to create a robust, scalable platform for industrial carbon capture and fuel generation that will pave the way for the future research. The fusion of biotechnology and engineering opens new avenues for clean energy and environmental resilience, setting the stage for a circular carbon economy.
Hello everyone, I'm Çağdaş. I will discuss methodology. Our proposed methodology is designed to be both scientifically robust and practically feasible. The project is structured around three key elements: strain optimization, bioreactor design, and field integration. We will use CRISPR-based techniques to enhance hydrogen production and stress tolerance in cyanobacterial strain UTEX. These enhancements will help the strain survive and function efficiently under real industrial flue gas conditions. In parallel, we will design and prototype custom photobioreactors using CFD modeling to optimize light penetration and gas exchange. These reactors will be modular and adaptable for integration with actual industrial exhaust systems. Also, we plan to access laboratory facilities and prototyping tools through collaborations with academic research labs and industry partners. So, does the timeline fit all the plans? Research and experimentation span from 2026 to 2027 to allow time for genetic modification of cyanobacteria and validation of improvements like CO2 capture efficiency and solar to biomass conversion. These biological processes require iterative testing and environmental simulations. Additionally, the one-year application phase focuses on prototype development and industrial testing, which demand careful integration with real exhaust systems. Our strategy focuses on combining synthetic biology with systems engineering to achieve measurable, impactful results. The choice of CRISPR as a gene editing tool allows us to make precise improvements in metabolic pathways targeting increased hydrogen production. We selected UTEX because of their own productivity and resilience. Their rapid doubling time and high light utilization make them ideal candidates for industrial bioconversion. The bioreactor design is equally strategic. Instead of using generic systems, we are creating reactors optimized for industrial scale integration. This includes modularity for easy installation and tailored light and gas exchange properties. Our estimated budget is approximately $1 million. First, a portion will be used for lab scale work and genetic engineering, covering CRISPR tools, growth chambers, and strain cultivations. Second, a significant share will go towards bioreactor prototyping and testing, including CFT modeling, material fabrication, and sensor integration. Finally, we will dedicate funding to field application and pilot testing, which involves transportation, installation, monitoring equipment, and potential collaborations with industrial partners. To summarize, our project offers a sustainable and innovative solution to industrial carbon emissions by using engineered cyanobacteria to convert CO2 into clean biofuels. We combine advanced genetic tools and real-world partnerships to ensure feasibility, scalability, and impact. With measurable performance goals and a strong interdisciplinary team, we are well positioned and deliver a prototype that is not just scientifically exciting, but also industrially relevant and economically effective. We believe this project aligns with the future of green energy, and with your support, we can make this vision a reality. Thank you for listening.